Okay. We've been talking about the factors that influence sediment accumulation in the basins. We talked about the tectonic origin earlier in the semester. Now we are looking at the effects of a number of variables that influence the accumulation of sedimentation. And as we see as we go on tonight, we are talking about the combined effects of rates of subsidence, relative sea level change, and rates of sedimentation. And those are the three main variables that interact to give rise to the different packages that we see in the sedimentary basins. Obviously, various aspects of the sedimentary basins themselves impart a signature onto the sediment package as well. We talked about this briefly last time, the geometry of the basin and so on and so forth, related to its tectonic development. But these three other factors, these three variables, if you want to think of them that way, are particularly important in terms of determining thickness of the stratigraphic sequence, breaks in the stratigraphic sequence, these kinds of things that go on. And one of the things that we were talking about in class last time was the effects of climate in terms of large-scale sea level changes, and how obviously those sea level changes will influence the development of different packages of sediment. And most of you should be familiar by now with the fact that the planet has undergone multiple climate changes in the geologic past, but there are basically only two climatic states that the planet exists in, the icehouse climate and the greenhouse climate. And again, when we talk about things like denudation and the origin of sedimentary materials, we saw the importance of climate in terms of how that influences the origin of sediment. And as we see in this part of the class, the effects of climate change on the larger sedimentary package principally related to sea level changes, and principally many of those changes can be fairly rapid depending on climatic circumstances. So if we look at the icehouse climate and what characterizes the icehouse climate, and we are currently living in an icehouse climate. Obviously, we are living in a significant warm period within that icehouse climate, but nonetheless, the planet is still experiencing that large-scale climatic characterization. And the icehouse climate is characterized by strong latitudinal temperature gradients. In other words, when you go from the equator to the poles, there is a significant and major temperature gradient. Now, as we see when we look at the greenhouse climate, you similarly have a latitudinal temperature gradient. It's going to be warmer at the poles, at the equator than at the poles, obviously, but the significance or the extent of the gradient of that change is significantly different. Again, as you might imagine, you have low mean ocean temperatures in the icehouse climate, and this in part then leads to very active, strong active oceanic convection, where surface waters are heated and you have waters near the poles cooling and subsiding, and this drives a very active oceanic convection system, which has the effect of giving rise to highly oxygenated oceans, so that deep ocean waters are reasonably well oxygenated because of the very active convective circulation patterns driven by these icehouse climatic conditions. And of course, perhaps most convincingly, in terms of identifying the climatic state, the presence of significant continental ice caps and sea ice. Sea ice obviously in the Arctic and the Antarctic continental ice cap that we saw in our discussion in class last time. So those are the principal characteristics of an icehouse climate. And as you can imagine, when you flip to the greenhouse climate, you essentially see the reverse. You have weak latitudinal temperature gradients. So there is a temperature difference, obviously, between the equators and the poles, but the extent of that difference is somewhat diminished. The ocean water temperatures are going to be significantly higher, obviously, and because you don't have the temperature contrast developed in the world's oceans, you don't have the same degree of oceanic circulation. And in fact, ocean circulation gets to be quite sluggish during the greenhouse climate, and this leads to anoxic marine conditions because the oxygenation of the waters at the atmosphere-ocean contact is important, obviously, for the absorption of oxygen. If you then take that water and circulate it vigorously throughout the system, that oxygenated water gets to the deep ocean and other places in the ocean basins, giving rise to conditions that, one, affect, obviously, the organisms that live there, and two, they affect the sediments that accumulate. So a lot of the black shales, for example, that we see in the stratigraphic record, if you look at the Phanerozoic as an example of stratcolumn of Phanerozoic, which we will a little bit later on, and you look at the distribution of black shales, you see that it's no accident that significant thicknesses of black shales exist or were deposited during times of the greenhouse climate, and they represent the trapping of significant amounts of organic material because of the anoxia that existed at the time of their deposition. And then, of course, finally, quite logically, you have warm polar regions and you have no ice, sea ice or ice caps. And this gets into some interesting discussions in detail because I know in talking with Dr. Bhattacharya, there are arguments about there being brief periods of glaciation during the Cretaceous, for example. This is indicated by some stratigraphic information that they've got, but there is no record, no consistent record that I know of that would suggest the strong evidence in favor of icy conditions during the Cretaceous. But so whether or not there are relatively small scale, I'm talking here in a time scale sense here, little excursions where you get cooler periods. We had the Little Ice Age in the northern hemisphere, which lasted 400 to 600 years or whatever it was in the 17th and 18th centuries, I think it was. So we know that looking at shorter time intervals, that there are excursions to warmer and colder intervals. But the large-scale picture obviously is tied to these two major climatic conditions. So then you get into the question of why does the climate change? The dinosaurs didn't drive around in SUVs, and so you can't blame the SUVs for global warming in the Cretaceous. So clearly there are natural phenomena at play here that drive the climate one way or the other. And what we are seeing today, of course, is anthropogenic driving of the climate because we are taking the sediments that were deposited in the anoxic conditions of past greenhouse climates, and we are releasing that carbon dioxide by burning the oil and coal and the other preserved organic material. So if we look at kind of general causes for climate change, there are astronomical variations